So, last 2 days we're going to talk about an extremely important idea. This is the notion of compactness. Compactness. If you go on and do anything involving analysis, you need to know what compactness is. Okay. Now the definition, so like we said last time, compactness is some sort of quality of finiteness for an infinite set. Okay, it sort of makes your set, you have an infinite set, but if it's also compact, then it has some degree of finitude, if that's a word. I think that's a word. Okay. Okay, so, but the definition of compactness is a little bit hard to get one's head around. And it starts off with something called an open cover. Okay, so let E be a subset of R. Any collection of open sets, G sub alpha, such that E is contained in the union of the G sub alpha, is called an open cover of E. Okay. Called an open cover of E. Okay, so for example, if I have a set 0, 1, right, the open interval 0, 1, right, I could take itself, without, if I let G1 be 0, 1, then this collection is an open cover of 0, 1.
Wait, can you repeat that?
Right, so here I've got the open interval 0, 1, okay? And I just use that entire set as one of my G alphas, okay? I let G1 be the set 0, 1. Well, then my set E is contained in the union of the G's, right? It's covered by this one guy, right? So, you know, that's an open cover. Okay. Or let's say that E is the real line. Okay. Suppose that E is the real line, and I take let Gn denote the interval n plus 2. Okay. So I've got the real line. And for example, G0 would be the interval 0, 2, right? G1 would be the interval 1, 3, right? G2 would be the interval 2, 4, and so on and so forth, right? G negative 1 would be negative 1, 1, etc., etc. Okay? And you see that the union of all these guys, the union of the Gn's, as n ranges over all the integers, right? This thing is since R is contained in that union, right? Then these guys, this set is an open cover of R. Okay, you guys getting this right? It's just a bunch of open sets whose union covers the set, right? Anything like that is called an open cover of the set. Okay. Notice that sets can have lots of open covers, right? I could have covered R in billions of ways, lots, infinitely many ways, right? And I can make up open covers of R however I feel like, right? I could go like this, right? Here's G1, G2, G3, etc., etc. I could take them expanding, whatever. Here you can do however you feel like. Okay. 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 So every, you could cover this in lots of ways. Okay. So now we come to the definition of compactness. So this is the weird one. So let K be a subset of R. if K has the property that every open cover, that given any open cover G alpha of K, there exists a finite what's called a finite subcover, G alpha 1 through G alpha n, that still covers K. Maybe I should say like a finite I'm going to just think of that finite subcover that still covers K. Then we call K a compact set. Okay, so in other words, there exists a finite set of indices, A1 through AN, such that the union of the AI from I equals 1 to n still covers K. Okay, so and K is a compact set. Okay. So I'll say it again. I'll say it in English. Well, I'll wait for you guys to finish copying first, and then I'll say it. Copy faster.
You can go ahead.
Okay, so let me say it in English, right? So a compact set has this weird property that whenever you have an open cover covering it, there is a finite subcollection of that cover. You can choose this finite. You can find finitely many of those guys that still cover the set. Okay. Okay. So let me make the dumbest example of a compact set. Right. So the dumbest example. Say that K is a single point. Right. K is a single point. Okay. Then this K is compact. Right? Because here I've got my single point X, right? And suppose somebody says, I'm going to give you an open cover. I give you an open cover, let's say that G alpha is an open cover of K, right? That would mean that you've got these bunch of guys and that X is contained in the union of the G alpha, right? Well then, just one of the G alpha must include X. So call that G alpha 1. Okay? Then the set consisting of that one set is a finite subcover. Okay. Right. So somebody says, okay, let me give you an open cover of X. Here my G. Here's my G1, G2, G3, right? G4, G5, whatever, right? And they give me an open cover, and you say, okay, can I find a finite subcover? Well, just if one of these guys has to include X, choose that guy and use that guy as your cover, right? Use that guy as your finite subcover. So, if you've got a single point, of course that's compact. Or if you've got finitely many points, that's also going to be compact, right?
Could you go over just very quickly in English the meaning of open cover one more time?
So open cover is just a bunch of open sets that covers your set.
Okay.
Okay.
Entirely.
Yeah. It has to cover all of your set. Okay, so
one individual open cover covers all of the set, or the collection of all of the individual covers, open covers.
Again, let's go back to the example. Right, here's R. Okay, and we let G sub n be the interval negative n and the same. Okay, for n equals 1 to infinity. Right. Okay. You notice that R is contained in the union of the G sub n's. Right? G1 is the interval of negative 1, 1. G2 is the interval of negative 2, 2. G3 is the interval of negative 3, 3. Right? They're expanding. Right? And you see that R is contained, if you take all of these guys, then R is contained in their union. Okay, so this thing, the collection of all these guys is an open cover of R. Okay? But notice, no finite subcollection of the Gn still covers R. Right? Right? No finite subcollection is going to cover R, because if you take only finitely many guys, well, take the biggest one, there's still stuff on the outside. Right? So you see that R is not compact. R is not compact. Okay. Right? Because compactness means that whenever anybody gives you an open cover, you can find a finite subcover that still covers. Okay. People sometimes say a decent finite subcover, in the sense that it covers a subcover that still covers the set. But anyway. Okay. So here we are given here we found an open cover, but there was no finite subcover that worked. Okay. Now I could mess this up. I can make a cover that has a finite subcover, right? I could say I'm going to let G0 be all of R. Okay. Right? In that case, if somebody says, do you have a finite subcover? I say, yeah, here it is. The set containing G0. Okay. So, I can make open covers that do have finite subcovers, but you have to be able to have finite subcovers no matter what open cover you're given. Okay. So here, you see that R is not compact, because we're able to create something that doesn't have a finite subcover. Okay, let me give another example. Okay. 0, 1, the interval 0, 1 is not compact. 0, 1 is not compact. Find an open cover that does not have a decent finite subcover. Can you think of a collection of open sets that covers 0, 1, but there's no finite sub-collection of that covers 0, 1? Can anyone come up with one? I don't want to spend too much time on this, but can anyone see one immediately? Bunch of open sets whose union covers 0, 1, but for which no finite subcollection still covers 0, 1. Let me just give it to you. Okay, so you could let, for example, G sub n be 1n comma 1, 1 over n comma 1, for n being 2 onwards. Right? And you see what's wrong with this. I mean, you see the trouble. Right? The union of these guys does cover 0, 1. Right? Here is 0, and here is 1. Right? The first guy goes from 1/2 up to 1. The second guy goes from 1/3 up to 1. The third guy goes from 1/4 up to 1, and so on and so forth. Right? And you see that their union, the union of the GNs, actually is all of 0, 1. Right? But if you take any finite subcollection of these guys, well, there's going to be some gap between 0 and 1 over the largest number. Okay, so 0, 1 is not compact. Okay, is that clear? Making sense what compactness is? It's kind of a bizarre definition, right? No matter what open cover you're given, there's a decent finite subcover.
And by decent, you just mean that it
Still covers the set. I don't need to say it. I guess it's the word decent is contained in the word cover, basically, right? If I say finite subcover, I mean it's still covering. It's redundant. Okay. I'm going to make a remark, but I'm not going to prove it at this point. The interval 0, 1 is compact. The closed interval 0, 1 is compact. Right? And this is related to what we said last time. What is it about 0, 1 that makes continuous functions attain a max and a min on it? Right? What is it about 0, 1 that makes the extreme value theorem work, but 0 doesn't work on the open interval 0, 1? It's actually this quality of compactness. Okay, so properties of compact sets. Okay, so I'm going to start off with one just as a remark because it's so trivial. Compact, so say that we're in R. Okay. Compact implies bounded. Compact implies bounded. And the proof is as follows. So K compact implies that K is bounded. proof. Consider G sub n being negative n for n equals 2 onwards. Then the union of the G sub n's covers K. Right? Because the union of the G sub n's covers all of R. Right? So it's definitely going to cover K. Right? Well, if K is compact, right? K compact implies that there exists some finite subcover. There exists N1 through ND, such that K is contained in GN1 union G and D. But then let's say that then K is contained in the union, then K is contained in the largest one. Right? These guys are intervals centered at 0, right? So there's -1, negative n1, positive n1, right? There's maybe negative n2, positive n2, blah blah blah. Just take the biggest one, right? K is contained in that largest one, right? But that means that K is bounded, right? Because it's contained in an interval, a finite interval. So compactness implies bounded. You cannot be an unbounded set and be compact. Okay. Now something a little bit more meaty. Compact. So K compact implies K is closed. K closed, and remember what closed means. Closed means that the complement is open. Okay. So you have to be a closed set if you're compact. Okay. So we want to show that K complement is open. Pick a point in K complement. What do we need to do to show that K complement is open? Well, we need to show that if you pick any point in it, then you can find a delta neighborhood around P that's contained in that set, right? So you have your set K, you have your point P that's outside, and you want to show that you can find a delta neighborhood in which that contains P and is in the complement of K. Okay, so we're gonna make one. Okay, and we're gonna do it in kind of a kooky way. Okay, you'll like it. Okay, so you say, well, okay, for each point Q in K, let R sub Q be the distance between P to Q divided by 2. Okay, so I take, here's my point P. For any point Q in here, I look at the distance between them, and I take half the distance, and I call that thing r sub q. Half the distance between p and q is what I'm going to call radius sub q. Then you see that, notice that the neighborhood of radius RQ around Q and the neighborhood of that same radius around P don't intersect each other, right? So I take this neighborhood and this neighborhood, then they don't intersect each other. Maybe you need to prove that, but it's easy. Okay. Okay, and now what we're going to do is cover K with the NRQ Qs. Okay. So for every point in K, we're gonna make that R sub Q neighborhood. Every Q in K, we make that R sub Q neighborhood. Some of them will be big, some of them will be small. Right. If this is my point, right, then this right neighborhood will look like that. Okay. So depending on how far you are, the radius changes. Okay. So okay. So now since K is compact, right? You know what I'm going to do. I'm going to use compactness. I've got my open cover. There's going to be a finite subcover. Right? In every compactness proof, there's this step. You go from the open cover to the finite subcover. Right? Since K is compact, we know that there exists a finite subcover, i.e., there exist Q1 through Qn such that K is contained in n Q1 union n Qn. Okay. Right. You know that there's a finite bunch of points whose the union of whose neighborhoods covers K. Okay. Okay. Let R be the minimum of RQ1 through RQn. Right. So take the smallest radius. Right. You see that you're going to get a bunch of radii. Take the smallest one. Take the smallest one. Okay. Then the neighborhood of that radius around P does not intersect any of the NQIs. Right? right? But then, and thus, does not intersect K, right? Because K was contained inside of those NQIs, NQIQIs, right? Right. So P is contained in NRP, which is contained in K complement, and thus K complement is open. Okay, any questions, Marco? Nope.
No, I think just a remark. So the most important reason why we needed the compactness is so that we could make that set finite,
Exactly.
so we can take a minimum. Right?
Exactly, right? Because if it's not compact, then that radius could become 0, right? Then that radius could become 0, and then we're in trouble, right? Because then you've got a neighborhood of radius 0, which is not an open neighborhood, right? Right. The picture would be like this. Suppose this is our K, and we choose a P right on the edge of it. Okay? We choose a P right on the edge of it. Well then, the radii could become infinitely small, right? The radii would become infinitely small, and then we run into trouble. Okay. You guys seeing how the compactness arguments are working? Let's do a few more. So some theorem. Suppose that you have a K contained in R and K is compact. I've seen some people use this notation, right, to indicate compactness. They use this sort of double thing. If you see it, that's what it means. I don't use it. Okay. Suppose that you have a set contained inside of a compact set. Okay. Suppose you have a set contained inside of a compact set. If F is closed, then F is also compact. Okay. So anytime you have a closed set sitting inside of a compact set, that closed set is also compact. People use F for closed sets because of the French word for closed. Okay, so any closed subset of a compact set is still going to be compact. Okay, so the proof of this is not too hard. Okay, so suppose that GA is an open cover of F. We want to show that we want to show that F is compact. So take an arbitrary open cover. We need to show that we can get a finite subcover. Okay. So we have an open cover. So we've got K here. We've got F sitting inside of K, and we have a cover of F. We have a cover of F, the G alphas. Okay. Then, if we include F complement in the G alpha. So maybe, how do I say this? So we make an open cover of K as all the G alpha union the set F complement. Right? Notice that F complement is open since F is closed. Right? So you see that if we throw in F complement, we're going to get a cover of K. Because the G alpha is covered F, and F complement covers everything else. So we got an open cover of the compact set. You know what we're going to do? We're going to get a finite subcover, right? K compact implies there exists a finite subcover of K. Okay. And thus of F okay. But the trouble is that the finite subcover might have this F complement in it. We don't want that F complement in it because that wasn't part of our original cover. So remove it. Removing F complement from that collection yields a finite cover of F.
Why did you just do that? Why are you removing it?
Because we created a different open cover. We created a different open cover for K. We had an open cover of F. We want to see that there's a subcover of this that covers F. Okay. We create a different open cover of K. Okay. There's a subcover of this guy that covers K. Right? But that subcover is not a subcover of this, it's a subcover of this. Okay? I throw this guy out. Right? I look at that subcover and I throw the FC out if it's there. Okay? Now I've got only G alphas. Right? And so now I've got a subcover of the G alphas. Right? That's what I needed. Yeah, Aria.
So maybe like an intermediate step would be like alpha sub 1 all the way to alpha sub n is enough to cover, union F complement is enough to cover K, and so therefore, like, is that kind of the idea?
Well, so it would be something like this. G alpha, K is contained in G alpha 1 union G alpha 2 union G alpha n union possibly F complement.
Mm-hmm.
Okay. Okay. So then remove FC, right? And you see that then F is contained in G alpha 1 union G alpha n, and thus we have a finite subcover of F. Yeah. I mean, the thing is that I don't know if FC may be in there or may not be in there. Like, it may be that one of the G alphas is huge, right? And this is one of the G alphas. And so FC wasn't even included. Okay, but if it is included, then you remove it. Okay, so you've got this closed subset of a compact set. Somebody gives you an open cover of it. You create an open cover of the compact set by including F complement, right? Compactness says, well, then there's going to be a finite subcover that covers K. Throw out this F of C anyway, because you don't need F of C to cover F, right? FC is a complement of F. Doesn't cover F at all. So throw that guy out, right? Throw that guy out. You're left with the G alphas. Those guys cover F, right? Because these guys plus FC covered K, and this thing didn't cover any part of F, right? So throw those guys out. Throw that FC out if it is in there, and then you get you get a bunch of G alphas that cover F. In other words, a finite subcover. Okay. Okay, we don't have time to do the hard one, so let me do the easy one. Okay, so another theorem. If K is compact and E a subset of K, an infinite set, then E has an accumulation point. Any infinite subset of a compact set has an accumulation point. In some texts, this is called a limit point. And this quality is called limit point compactness. Limit point compactness. So what we're showing is that compactness implies limit point compactness. Limit point compactness, any infinite subset has a limit point. Let's prove it, since it's short. Okay, so we do it by contradiction, saying, well, suppose no points of K are accumulation points of E. No points of K are accumulation points of E. But that would mean that then for each Q and K, there exists a neighborhood, an open neighborhood, V sub Q, containing no other elements of E, except possibly like Q itself, the center. Let me say no elements of E, except possibly Q. Right? Nobody's an accumulation point, right? So everybody has a neighborhood in which there's nobody of E except maybe the center. That's what it means to not be an accumulation point. Okay, so everybody has some neighborhood, and there's nobody of E inside there except for possibly the center. Okay, but then then no finite right, notice that the V sub q cover K. Right, we've got these neighborhoods, we cover K with these guys. Right, but that would mean that there's a finite subcover. There exists some VQ1 to VQN that still covers K. Right, there's this finite subcover that still covers K, but then they would cover E, right? Because E was contained, E was a subset of K, right? But then E is contained in the union of these sets, each of which contains at most one point of E, right? So E is a finite set, but it's a contradiction. E was infinite, right? So E is finite.
So we use the fact that K is compact to say that there's infinitely many V sub Q's that cover K.
Exactly.
And then each of those V sub Q's can contain only,
One
at
point.
most, one element of E.
Exactly.
Wow.
Why the wow?
I don't know, it's just kind of like, who would have thought?
Yeah, it's cool, right? It's kind of a nice argument. Yeah, this is how one argues with compactness. It's fun it's fun once you get used to it. Okay. Okay, that's it for today.